In this video, we're going to do 3 manipulations in a concrete example of a vector field. We're going to test to see whether the vector field is conservative. We're going to say if it's conservative, how do we find its scalar potential function? And then finally, we're going to use that scalar potential function to evaluate a line integral. What's really going to be new in this video is the methodology behind finding the scalar potential function. Okay, so let's dive in. I have this vector field here. It has a I hat component, y cos x plus y, a j hat component, sin x plus x, and a k hat component, just 1. And I'm actually going to come here and I'm going to label these 3 m, n, and p so that I can refer to them a little bit more simply later on. So our first goal was testing to see whether it was conservative. And we had seen in the previous video a test for conservative. It was about comparing a bunch of different partial derivatives. So the first thing I'm going to do is take the partial derivative of m with respect to, say, y. So I'm looking at m and I'm taking this partial derivative with respect to y. So y cosine of x, partial with respect to y is just cosine of x. The derivative of y with respect to y is just 1, so I just get 1. And then this was the partial derivative of the first component with respect to the second variable. So the thing that I compare that to is the partial derivative of the second component with respect to the first variable. And indeed, you can check that the partial derivative of n, which is sin x plus x, with respect to x would be cos x plus 1 as well. In other words, the thing that needed to happen to be conservative has indeed happened. Okay, I've given myself some space and I'll do a similar computation. Now I'll take the partial derivative of m with respect to, I don't know, how about z? I want to end up doing all the different ways that I can mix and match these partial derivatives. Anyways, partial derivative of m with respect to z. Well, in fact, there is no z appearing anywhere in the m, so that's just going to be 0. And similarly, the partial derivative of p with respect to x, well, p was just 1, so this derivative is 0 as well. The second equality that needs to be true has also been verified. And then very quickly, for the final one, the partial derivative of n with respect to z is once again 0. There just is no z inside of the n. And the partial derivative of p, which is a constant with respect to anything, in this case it's y, is also going to be 0. And so the 3 different things that needed to be checked for being conservative are true. So this is a conservative vector field. Now, the big implication of being a conservative vector field, the reason why I performed that quick check, is because this implies that the vector field f can be written as the gradient of a scalar potential function, a little f. But how? That's my big question mark. I am saying it must be able to be written this way since I've tested to see whether it's conservative, and yes, it's conservative. But how do I find that scalar potential function? That's the methodology we're going to focus on in this video. So the first step forward is I'm going to expand this gradient of f. The gradient of f can be written as the partial derivative of f with respect to x. That's what's going to happen in the I hat component. The partial derivative of f with respect to y in the j hat. And finally, the partial derivative of f with respect to z in the k hat. That's just the definition of the gradient vector. But we already have some terminology for the first, second, and third component of my vector field f, namely the m, the n, and the p. So what this means is that the partial derivative of f with respect to x has to be equal to m. The partial derivative of f with respect to y has to be equal to n. And the partial derivative of f with respect to z has to be equal to p. So this is the key hook that I'm going to use to try to come up with my f. Effectively, I've got 3 derivatives, and so I'm going to try to, in effect, do some integrals to come up with what my function f is. So let's focus on the left one first, the partial derivative of f with respect to x equaling to m. And m I've written up here is y cos x plus y. So let me give myself some space here. In other words, I'm saying the partial of f with respect to x was equal to, what did I just say? Y cosine of x plus y. So if I want to figure out what the f is, I could just integrate both sides of this. This is an integral with respect to x. And so this is going to give me that f is equal to y times sine of x, because the integral of cosine of x is sine of x. And then y times 1, if you will, integrates to y times x. So this is going to be times yx. This is all fine, but I haven't dealt with a constant. As you know, when you take an indefinite integral of something, you get a function plus a constant. But what's particularly important here is that this is a multivariable function of x, y, and z, and I was taking the partial derivative just with respect to x. And thus, the constant that I get is a constant function with respect to y and z. In other words, what I'm implying here is it is something where the partial derivative with respect to x is 0, but any function that only depends on the other variables, y and z, will have that property. So the constant is not a constant, it's an entire function of y and z here. So that's great, but how do I find that? Well, let me take this and plug it in now to the second of these components. As in, I now have a partial derivative of f with respect to y is equal to the value of n. So let's do this. I'm going to take the partial derivative of f with respect to y. This is relatively straightforward to compute. Y sine x just takes a derivative to become just sine x. Yx is just going to become x. And then finally, here I have the partial derivative of this function c of y and z with respect to y. That's my three different components. Now, this, it's claimed, is equal to n. That is, the partial derivative of f with respect to y is n. And what was n? Let's just scroll up because I've forgotten. N was sine x plus x. So we'll come back down. And this is claimed to be equal to n, which is sine of x plus x. That was my n. Okay, so you have sine of x plus this derivative of this function c of y and z is equal to sine x plus x. There's a sine x plus x on both sides. And thus, what we've deduced is that this must be equal to 0. Okay, now, so what does that mean? We're saying that the partial derivative with respect to y is 0. Thus, what we're saying is it is a constant with respect to y. It does not change in y at all. So really what we're saying, what this computation showed, is that the function c, which is a function of y and z, is actually only a function of z. Because the partial derivative with respect to y is 0. It just only has a constant dependency on the y. So it's just a function only of z. And so let's try writing that down now. What we've deduced is that our function f is the y sine of x plus yx that we had seen earlier when we were sort of focusing back up there. But instead of adding a function of y and z, I'll just write it c now only of z because I know there is actually no dependency on the y. Okay, final thing I should do is now take the partial derivative with respect to z. That was the third option, and that's going to be equal to p. So partial derivative of f with respect to z now is, well, 0 plus 0 plus c prime of z. And the claim is that this must be equal to p. So let's go all the way back to the beginning. Remember what our p was. Our p was 1 in the original vector field. So in other words, we're saying that this all has to be equal to 1. So c prime of z is equal to 1. And that now lets me write down my f is y sine of x plus y of x plus, well, if the derivative with respect to z is 1, the original c of z is just equal to z, so plus z. And then I still have the option of having a plus a random constant, and I have no way of determining what that constant is. I still have the same plus c that we always have when we're trying to integrate indefinitely. As we see in a moment when we go and do line integrals, it doesn't actually matter what the value of the c is, so I'm actually just going to leave my box right there and assume that my c is equal to 0, or at least take the choice, the arbitrary choice that my c is equal to 0. So, okay, so what was this methodology effectively doing? It was saying once you knew that a vector field was conservative because you performed the test with the partial derivatives, but then the basic method was that you'd integrate, say, with respect to x, you'd get this constant in terms of y and z, you'd differentiate that and compare it to what you had, you'd then integrate it back again, and you kept on doing this sort of cycle of differentiation and integration so that you could play around with that constant and finally get out what this function was. All right. So I have my f, and let's return back to the original problem as I phrased it, which was my goals for this video. I wanted to test for conservative, I've done that. I wanted to find a scalar potential function if I knew it was conservative. Thirdly, I want to compute a line integral. Well, what line integral? I guess I get to make it up here. So I am going to put that right there and give you the following example. Okay, so I'm asking you to compute the line integral of f dot dr for some curve that I haven't really specified other than telling you what the endpoints are. The one endpoint is 0, 2, 1. The other endpoint is pi 1, 3. So I couldn't actually solve this via our old methods of, say, parameterizing a curve because I haven't told you which of the many different curves it's going to be. So our method thus has to be using the fundamental theorem of line integrals. And it says if you have a conservative field where your vector field f can be written as the gradient of a scalar potential function, then it's fairly simple. All it is you evaluate at the difference of the two endpoints. So I'm going to evaluate it at the second point where it finishes pi 1, 3, and subtract off the value of the function 0, 2, and 1. And, well, I know the f, because that's what we just spent all this time computing. So, okay, I have my f just above, so this is going to be equal to y is 1, then sine of x is just going to be times 0 plus 1 times pi plus 3. So that's going to be what it is on the left-hand side. And then I'm subtracting off, okay, so it looks like the x is 0, so I'm going to subtract off a 0 term. I'm going to subtract off a 0 term, and I'm going to subtract off a 1. Final answer, pi plus 2. And the point isn't really the answer. The point is, look how easy the fundamental theorem of line integrals made this computation after you knew that the vector field was indeed conservative. You did this rigmarole of finding the scalar potential function, and, well, that can be a little bit obnoxious, but it's just this computation. But once you have that computation, and you only need to do it once, you can now do every single line integral just trivially here, because you just apply the fundamental theorem of calculus. If you know the endpoints, just evaluate them. It doesn't even matter what the curve is. I don't even need to specify it in the particular problem. All right, so I hope you enjoyed this video. If you did, please give it a like for the YouTube algorithm. If you have any questions about this video, leave them down in the comments below, and we'll do some more math in the next video.